Hello, we discussed different nuclear properties such as nuclear charge, nuclear radius, nuclear mass, nuclear density, binding energy, nuclear angular momentum, and nuclear spin. Also, we explained binding energy curve and the various terms involved in the semi-empirical mass formula. In the present session, we start with the seventh nuclear property, that is nuclear electromagnetic moments. The nuclear electromagnetic moments, they are of two types, the nuclear magnetic dipole moment and nuclear electric quadrupole moment. Nuclear magnetic dipole and the electric quadrupole moments, they have similar importance in helping us to interpret the nuclear structure. Now, any distribution of electric charges and currents, they produce electric as well as the magnetic field, which in combination are called the electromagnetic fields, and they vary with the distance, or we can say that they have the spatial dependence. So it is necessary to assign the charge and current distribution and electromagnetic multiple moments. So we can say that the electromagnetic multiple moments, they are associated with the spatial dependence, means they vary with the distance. If we have 1 upon r square, then electric field arises from the zeroth or the multiple moment, monopole moment, zeroth or the monopole moment. If we have 1 upon r cube, it means that electric field arises from the first or the dipole moment. And if we have 1 upon r4 dependence, then the electric field arises from the second or the quadrupole moment, and so on. So one important point to remember here is that the magnetic monopoles, they either do not exist or they are exceedingly rare, because magnetic poles, they always exist in pairs. Now, another restriction on the multiple moments come from the symmetry of the nucleus and is directly related to the parity, okay, of the nuclear state. Each electromagnetic multiple moment has a parity determined by the behavior of the multipole operator. So the parity of the electrical moment, it is given by -1:L, and the parity of the magnetic moments, it is given by -1:L, L plus 1. So first we talk about the parity of the electrical moment. So here in this case, if L is even, then we have even parity, and if L is odd, then we have odd parity. So here we will have electric monopole, then electric dipole, then electric quadrupole, and then electric octopole, and so on. Now we come to the second, that is parity of the magnetic moments, that is -1:L plus 1. So in this case, if L is even, suppose L is 2, then our parity is odd. And if L is odd, suppose it is 1, then our parity is even. So here we will start from magnetic dipole, because we have said that magnetic monopole, they do not exist. So here there will be existence of magnetic dipole, then magnetic quadrupole, then magnetic octopole, and so on. Now, the conclusion is that all the odd parity static multipole moments, they all vanish. So vanish, which moments vanish? Here I try to write the moments which vanish. They correspond to L is equal to 1, that is electric dipole, then L is equal to 2 for magnetic quadrupole, and L is equal to 3, that is electric octopole, and so on. Now, the non-vanishing multiple moments are electric monopole, that is L is equal to 0, magnetic dipole, that is L is equal to 1, and the electric quadrupole, that is L is equal to 2. So, where L is the order of the moment, L is the order of the moment, and L is equal to 0 for monopole, L is equal to 1 for dipole, and L is equal to 2 for the quadrupole. Now we come to nuclear magnetic dipole moment. When a charged particle moves in a closed path, then it produces a magnetic field. So orbital and the spin angular momentum. When the particle moves, then it has two types of the angular momentum associated with, that is the orbital and the spin angular momentum. So the orbital and spin angular momentum of protons, since we are talking about the nuclear physics, within the nuclei it produces the magnetic field, which can be described in terms of the magnetic dipole moment located at the center of the nucleus, and it is denoted by mu. So here mu will be the contribution of both the orbital part as well as the spin part, and this value is E into h cross by 2 m into L, where L is the orbital angular momentum. The quantity E into h cross by 2m, this is called the magneton. Now, for electron mass, we generally use the Bohr magneton, that is mu b is equal to 10 to the power minus 5 electron volt per Tesla. But for the proton mass, because here we are interested in the protons, because we are inside the nucleus, we are talking about the nucleus, and within the nucleus we have protons and the neutrons. So here we are interested for the proton mass. So proton mass, we have nuclear magneton, and this value is 10 to the power minus 8 electron volt per Tesla, and mu n is always less than mu b. So in more useful form, we generally write mu is equal to GL, that is G factor, into L, that is the orbital angular momentum, and mu n, that is the nuclear magneton. And similarly, for the spin case, we can write GS, where GS, this is called the spin G factor, and GL, that is called the orbital G factor. GS into spin part, spin angular momentum, into mu n, that is the nuclear magneton. So in terms of orbital angular momentum, we have magnetic moment mu is equal to G into L into mu n, and in case of the spin part, we have magnetic moment is equal to Gs into S into mu n. So GL is the G factor associated with the orbital angular momentum, and Gs, this is called the spin G factor. For protons, we have GL is equal to 1 and GS is equal to 5.5 plus minus. This is the small value, small change in plus or minus in the spin G factor. And similarly for neutrons, GL is equal to 0 and GS is equal to minus 3.8 plus minus this small value. Now we come to nuclear electric quadrupole moment. Now, as we all know that nucleus is always considered to be the spherical, symmetrical in shape. So, if the nucleus is not spherical in shape, then the departure of the nucleus from the spherical symmetry, that is measured in terms of the quadrupole moment, and it is called the nuclear electric quadrupole moment, and it is generally denoted by Q, and its value is Q is equal to constant into B square minus A square, where B is along the y-axis, this is our y-axis, and this is x-axis, this is our y-axis. So B is along the y-axis and A is along the x-axis. So if Q is equal to 0, Q is equal to 0 means B is equal to A. So that means Q is equal to 0, so the shape will be spherically symmetrical. Now for A greater than B, Q will be negative, so the shape will be oblate. And if we have A less than B, A is less than B, then Q is equal to positive and the shape will be the prolate shape. Here I have shown the different shapes. So if Q is equal to 0, then we will have spherical shape. If Q is less than 0, then it is oblate shape, and if Q is greater than 0, then we have the prolate shape. So, spherically symmetrical nuclei, in case of spherical symmetrical nuclei, we can take the example of the oxygen nuclei, oxygen 16. Okay. In case of the oblate shape, we can take the example of sulfur 33. And in case of the prolate shape, we can take where Q is greater than 0, then we can take the example of aluminium 27, or even heavier nuclei having mass number 175. So this was all about the quadrupole moment. Now we come to nuclear parity, that is the 8th nuclear property. Parity of a nucleus, it refers to the behavior of the wave function as a result of inversion of the coordinates from x to minus x, y to minus y, or z to minus z. So for even parity, if the change of the coordinates, it doesn't changes the sign of the wave function, then we say that the parity is even. And if the change of the coordinates, it changes the sign of the wave function, then we say that the parity is odd. Parity has an important relationship with the angular momentum, and it is given by parity is equal to -1 is to power L, where this L is the angular momentum. So P is equal to +1 means P is equal to even for L is equal to 0, 2, 4, 6. Means if L is equal to even, then parity is even, and if L is equal to odd, suppose here we put L is equal to 3. So parity will be odd. So parity is odd for odd value of the angular momentum. Relation between parity and nuclear spin, this is also very important question from the examination point of the view. I is to power pi, where I is the angular momentum and pi is the parity. Okay, we can say that I is the nuclear spin, because in the last session we said that if we talk about the angular momentum, then we will say it is J, and in case of the nuclear spin we will talk about I. So here I is the nuclear spin and pi is the parity. So for the numericals, you can find out the different nuclear states, that either it is 0 positive state or 2 negative or 3 positive, different states you can find out. Now these are the methods of the measurement of the nuclear parity, that is nuclear reactions, analysis of the decay scheme, and electric and the magnetic movement. These are the different methods of the measurement of the nuclear parity. Now we come to the last nuclear property, that is nuclear statistics. Nuclear statistics, it is of two types, Bose-Einstein statistics and Fermi-Dirac statistics. So the particles which obey Bose-Einstein statistics, those are called bosons, and these particles have 0 or the integral spins. Okay, and the particles are alpha particle, photons, pions, deuterons, etc. Now the particles which have half integral spin, those are called the fermions, and they obey the Fermi-Dirac statistics. For example, electron, proton, and the neutron. So these were the different type of the statistics. So with this we have finished all the nuclear properties, different nuclear properties. So thank you so much.